Stars are supposed to follow rules. They are born when a gas cloud collapses under gravity, they ignite, they burn hydrogen for millions or billions of years, and then they die. We have equations that describe every stage of this process with extraordinary precision. We can calculate a star's lifespan from its mass. We can read its composition from its light. We can predict its death from its birth. The physics is not mysterious. It is built over more than a century of observation and mathematics, or so we thought, because scattered across this galaxy and beyond are 9 stars that have looked at every rule we have written and refused to obey. Stars that exist at times when existence should be impossible. Stars carrying elements that should have vanished billions of years ago. Stars burning inside other stars. Stars too heavy to be what they are, and stars too old to be anywhere at all. These are not rounding errors. These are not instruments malfunctioning. These are confirmed, measured, peer-reviewed objects. And every one of them is telling us that something in our understanding of physics is fundamentally, catastrophically wrong. These are the 9 stars that should not exist. Number 9. IRC plus 10,216. There is a class of star called a carbon star. These are aging giants whose outer atmospheres have become enriched with carbon, giving them a distinctive chemical fingerprint. In a carbon star, carbon dominates. And because carbon bonds aggressively with oxygen to form carbon monoxide, all available oxygen atoms are locked away. There is no free oxygen left to form anything else, certainly not water. Carbon stars do not make water. This is not a soft, theoretical preference. It is a direct consequence of basic molecular chemistry. In a carbon-rich environment, the conditions for water formation do not exist. The rule is absolute. In 2010, the Herschel Space Observatory turned its instruments toward IRC plus 10,216, one of the brightest infrared sources in the sky, a carbon-rich giant approximately 400 light-years away. The mission was routine. What it found was not. Herschel detected clear, unambiguous water vapor in the star's outer envelope, not a faint signal requiring creative interpretation. Water molecules radiating in the infrared, across multiple spectral lines. Scientists proposed that ultraviolet radiation from background stars might be breaking down icy bodies in the star's outer shell, releasing oxygen that then forms water. It is a plausible hypothesis, but that explanation means we fundamentally misunderstood the chemistry of carbon star atmospheres. Chemistry we had been confidently describing for decades, a rule we treated as absolute was not. This is the least terrifying star on this list. The universe broke a chemistry rule. It does worse things further up. Number 8, Mira. Omicron Ceti is one of the most observed stars in history. For centuries, humans have watched it pulse, brightening and dimming over a 332-day cycle. We understood it as a long-period variable star, an aging giant shedding its outer layers in its final billions of years of life. We thought we understood how stars like Mira lose mass through stellar winds, expanding outward in all directions, diffusing gently into the interstellar medium. It is a well-modeled process. In 2007, NASA's Galaxy Evolution Explorer, the GALEX ultraviolet space telescope, looked at Mira and found something our models had no room for: a tail, stretching behind the star for 13 light-years, a single, coherent, directional stream of material that Mira has been shedding for approximately 30,000 years as it moves at 130 kilometers per second through the interstellar medium. 13 light-years. The nearest star to our Sun is 4.2 light-years away. Mira is dragging behind it a trail of its own discarded atoms more than 3 times that distance. And it is not expanding in all directions, as our models said it should. It is streaming, directional, organized, like the wake of a ship moving through still water. Our models of stellar mass loss, models that feed into how we calculate stellar lifespans, stellar ages, and the chemical enrichment of galaxies, did not predict this. The star built something our equations did not allow. Number 7, blue straggler stars. Globular clusters are the oldest objects in the universe. These dense, gravitationally bound spheres of hundreds of thousands of stars formed billions of years ago from the same gas cloud at roughly the same moment. The stars in a globular cluster are contemporaries. They are the same age. This matters because stellar physics is unambiguous about one thing. A star's lifespan depends on its mass. More massive stars burn hotter, consume their hydrogen faster, and die sooner. In a cluster 12 billion years old, any star massive enough to shine hot and blue and bright on the main sequence should have exhausted its fuel long ago, should have swollen into a red giant, shed its outer layers, and left behind a cooling white dwarf. That is the trajectory. It does not have exceptions. In 1953, astronomer Alan Sandage was studying the ancient globular cluster M3 when he found stars that could not be there. Hot, luminous, blue main sequence stars. Exactly the kind that burn fast and die young, burning brightly in a cluster billions of years their senior. He called them blue stragglers. Since 1953, they have been found in essentially every globular cluster ever studied. Over 3,000 have been identified across hundreds of clusters. The currently accepted explanation involves stellar mergers and mass theft from companion stars, mechanisms that can, in principle, dump enough new fuel into a dying star to temporarily restart it. But this requires collision rates and binary interaction rates that our cluster dynamics models are still struggling to fully account for. The universe is producing rejuvenated stars at a scale our simulations did not predict. How many other processes are occurring at scales we have not calculated? Number 6. But this requires collision rates and binary interaction rates that our cluster dynamics models are still struggling to fully account for. The universe is producing rejuvenated stars at a scale our simulations did not predict. How many other processes are occurring at scales we have not calculated? Number 6. A stellar corpse, the city-sized, incomprehensibly dense remnant of a dead star, embedded in the living heart of a giant, slowly consuming it from within. The nuclear fires burning around a neutron star core would operate differently than standard stellar fusion, producing unusual elements in unusual ratios. For nearly 40 years, no such object was confirmed. Then, in 2014, astronomer Emily Levesque and her team examined HV 2112, a red supergiant in the small Magellanic Cloud, a satellite galaxy of the Milky Way. Its spectrum was wrong. The abundances of rubidium, molybdenum, and lithium were far beyond anything standard stellar nucleosynthesis in a red supergiant can produce. These were, precisely, the chemical fingerprints Thorne and Zhitkov had predicted a neutron star core would leave behind. The identification remains debated, but if AHV 2112 is what the spectrum suggests, then something previously consigned to theoretical speculation has been confirmed: a living star with a dead star at its center. Two stellar objects occupying the same space, one being slowly devoured by the other. The universe built a machine that physics said was possible, but that no one had ever seen. It waited 40 years for us to find it. Number 5. GW 190521. Stellar physics contains a forbidden zone. Stars whose helium cores fall between 45 and approximately 130 solar masses are predicted to undergo pair instability supernova. At the extreme temperatures inside these stars, gamma-ray photons spontaneously convert into electron-positron pairs, removing the radiation pressure that was holding the star up. The star collapses and then explodes, not in the way that leaves a compact remnant, but completely, annihilatingly. The entire star is destroyed. No neutron star, no black hole, nothing left but expanding gas. This is derived directly from quantum electrodynamics. It is one of the most robust predictions in stellar physics. On May 21, 2019, the LIGO and Virgo gravitational wave observatories detected a signal. Analysis revealed GW 190521, the merger of two black holes. The primary weighed approximately 85 solar masses. The secondary weighed approximately 66 solar masses. Their merger produced an intermediate mass black hole of 142 solar masses, the first confirmed detection of an object in this mass class. Both progenitor black holes fall directly inside the pair instability forbidden zone. By stellar evolution theory, both are impossible. The stars that formed them should have been completely destroyed. No confirmed formation mechanism exists for these objects. Physics wrote an explicit prohibition. The universe produced two objects that exist only in the band category. Number 4. SDSSJ 102915 plus 172927. When the universe was 3 minutes old, it contained hydrogen, helium, and a trace of lithium. Nothing else. The heavy elements, carbon, oxygen, nitrogen, iron, were forged in stellar interiors over billions of years and scattered across space by supernovae. The first stars produced the first metals. The second generation of stars formed from clouds enriched by those initial explosions. And the second generation was able to form because of those metals. Here is the critical point. Stars need carbon and oxygen to form. Not because carbon and oxygen are building materials for stars, they are not, but because these elements radiate energy efficiently, cooling the gas clouds that collapse under gravity. Without this cooling, the pressure in the cloud resists collapse. Without sufficient metal content, the physics of molecular cooling breaks down, gravity loses, and no small star forms.
Theoretical models have identified a metallicity floor, a minimum metal content below approximately Fe/H equals -3.5 to -4, below which star formation of this kind becomes physically impossible. In 2011, using the European Southern Observatory's Very Large Telescope, Elisabetta Kafau and her team measured the iron abundance of SDSSJ 102915 plus 172927. The result was Fe/H equals -5.07. Iron content more than 100,000 times lower than our Sun.
The star also falls below the minimum carbon abundance for alternative cooling pathways. By the cooling physics of molecular clouds, this star's natal gas was too pristine, too metal poor, too hot to collapse into a star of this mass, and yet the star is there. No explanation has resolved the contradiction. Number 3. PSRJ 0952-0607. When a massive star exhausts its fuel, its core implodes. The collapse is catastrophic and fast. Protons and electrons are forced together under gravity intense enough to fuse them into neutrons, and what remains is a neutron star, roughly the mass of our Sun compressed into an object the size of a city. A teaspoon of neutron star material would weigh approximately 1 billion tons, but neutron stars have a mass limit. Pack too much mass into one, and the neutrons themselves cannot resist gravity. The neutron degeneracy pressure, the quantum mechanical force that keeps the star from collapsing further, is overcome. The object collapses again, past the neutron threshold, into a black hole. This limit, the Tolman-Oppenheimer-Volkoff limit, is derived from general relativity and nuclear physics combined. Depending on the nuclear equation of state, how matter behaves under conditions more extreme than anything we can reproduce in a laboratory, the limit falls somewhere between 2.2 and approximately 2.9 solar masses. Above it, no neutron star survives. In 2022, a team led by Roger Romani at Stanford measured the mass of PSRJ 095 2-0607, a millisecond pulsar spinning 707 times per second, 3,200 light-years away. The result? 2.35 solar masses with an uncertainty of plus or minus 0.17. At its central value, this object is at or above the maximum allowed mass for neutron stars under softer nuclear equations of state. It has not collapsed. It is spinning 707 times per second and sending us radio pulses. Our equations say it should be a black hole. It is not. Number 2. Przybylski's star. In 1961, Polish-Australian astronomer Antoni Przybylski discovered a star so chemically abnormal that it has resisted 60 years of explanation. HD 101065 sits approximately 355 light-years away in the constellation Centaurus. When Przybylski analyzed its spectrum, expecting the standard signatures of iron, calcium, and silicon, he found instead a dramatic overabundance of rare earth elements, lanthanides and actinides, at concentrations that normal stellar processes cannot produce. This alone was strange enough. Then it got worse. Subsequent spectral analysis detected signatures consistent with short-lived radioactive isotopes, elements in the actinide series whose half-lives are measured not in billions of years, not in millions of years, but in years. Californium-252 has a half-life of 2.645 years. Einsteinium has a half-life of less than 1 year. If these isotopes were present when the star formed, even 5 million years ago, far less than its probable billions of years of age, they would have undergone hundreds of millions of half-lives of decay. Not a single atom should remain. They appear to remain. Something in or around this star is producing them continuously. No known stellar process can do this. The nuclear environment required would need to be unlike anything we have confirmed in any other stellar object. The star has been defying nuclear physics for as long as we have been looking at it, emitting elements that physics says cannot still be there. one star 355 light-years away, producing the chemically impossible, and we have no explanation. Number 1. The Methuselah Star. In the constellation Libra, approximately 190 light-years from Earth, there is a star that violates not a law of physics, but the most fundamental constraint in all of cosmology: causality. HD 140283 is a subgiant moving at 800,000 miles per hour through our galactic neighborhood. It is composed almost entirely of hydrogen and helium, with almost no iron, the chemical signature of an object so ancient it formed before the universe had time to forge heavy elements in significant quantities. In 2013, a team led by Howard Bond used the Hubble Space Telescope to measure its age with the highest precision ever achieved. They measured its distance, its oxygen abundance, and its stellar dynamics. The age they calculated was 14.46 billion years. The uncertainty margin is 800 million years. The universe is 13.8 billion years old. We know this with extraordinary precision from the Planck satellite's observations of the cosmic microwave background, the afterglow of the Big Bang. This is not an estimate with significant uncertainty. It is the hard limit of everything that exists. The moment before the Big Bang, there was no space, no time, no matter. There was nothing for a star to be made of. A child cannot be born before its mother. At the central measured value, the Methuselah star is 660 million years older than the universe itself. Even with the full 800 million year uncertainty margin applied in the most favorable direction, the star sits uncomfortably close to the universe's age, close enough that the tension remains in every calculation. Our stellar models may be wrong, our cosmological models may be wrong, or there is something about the origin of the universe that we have not yet understood. Either way, the star burns on. It does not need our explanation. It has been burning longer than time. These are not theoretical problems. They are not preliminary findings from a single paper waiting to be overturned. These are 9 objects confirmed through repeated observation, peer-reviewed measurement, and analysis by institutions and researchers across decades, and every one of them is pointing in the same direction. Our model of how the universe builds stars, from formation to composition to lifespan to death, is incomplete in ways we have not yet quantified. A carbon star that makes water tells us our stellar chemistry has gaps. A neutron star that exceeds the collapse threshold tells us our nuclear physics has limits we cannot yet see. A star older than the universe tells us that something in our most fundamental cosmological timeline is wrong. We did not find these objects by accident. We found them because we built better instruments, pointed them at the sky, and let reality show us what was there. The universe did not hide them. It has never tried to hide them. It has been producing them for billions of years in plain sight, waiting for us to look closely enough to understand that we were wrong. We have been studying stars since before recorded history. We have sent telescopes beyond the atmosphere, detected gravitational waves from across the observable universe, and mapped the echo of the Big Bang itself. And still, 9 stars refuse to fit. 9 points of light that the equations say should not exist, burning in the dark, indifferent to everything we thought we knew. The sky is full of things we have not yet understood. We are only beginning to realize how many.